Okay, thus far, we've used the Galerkin method in conjunction with the weak form of the equations of motion to get an integral equation that contained interpolation functions. And I want to talk in this lecture just specifically about those interpolation functions. So let me write down the equation that we obtained after applying the Galerkin method to the weak form. Okay, so let's just say recall. Applying the Galerkin method to the weak form of the equations of motion gave us the following. Integral over the volume of rho times our interpolation vector n ui double dot dv plus integral over the volume again, interpolation function vector comma j, so derivative with respect to x of j, c I j k l u k comma l dv, and that would be equal to integral over the volume of our interpolation function times b sub I dv plus the integral over the traction surface interpolation function times ti ds. Okay, let's call that equation 1. Okay, so I'll make a note here that we've written equation 1 over the whole domain, but equation 1 also holds true at the element level when we apply natural boundary conditions to the element. So specialize, that's with natural boundary conditions, right? Which is how we formulate elements, right? So we can then sum forces, and then we apply the displacements explicitly after. Okay, so with natural boundary conditions, remember those are forces. Okay, so within a single element, we want to approximate the displacement field. And we've shown this before, but we'll write it as u sub I, where I tells us the direction, x, y, or z direction. It's going to be a function of space, x, and t time. And we are going to approximate that as our interpolation functions, which will be a function of x, times our vector of nodal displacements. And I'll write that as ui. They'll be functions of t. And I'll put an e there to remind you that those are element level nodal displacements. Okay? So let me just define that in print here. Nodal displacements of the element in the ith direction. Okay, and we'll call that equation 2. So what does this n look like? And I know you have covered this probably in your previous classes, but this is one of those things that if you don't haven't seen it a few times, you tend to forget. So I'll just quickly go through an interpolation function at the 1D level, then I'll give you the interpolation functions at the 2D and for 2D and 3D elements. Okay, so let's just go ahead and consider a 1D element with some sort of a linear approximation. Okay, so in that case we have, here's an element, a 1D truss element in this case, and this is some point location x1, this is a location x2, and at the location x1 we have a displacement of that node u1, and we have a displacement of this node, call it u2. Okay, since it's a linear approximation, I want to say something like that u star, which is a function of x, is going to be equal to just a linear function, call it c naught plus c1 times x. Okay, and so right now c0 and c1 are our undetermined coefficients. We're trying to make it so that u1 and u2 are our undetermined coefficients. So we do that by solving for c0 and c1 in terms of u1 and u2. Okay, so that gives us two equations. It says that u star evaluated at x1 must be equal to u1. We're going to force that to be the case. And also that u star evaluated at x2 is going to be equal to u2. Okay? And we'll collectively call these equation 3. So we have two equations and two unknowns, right? Here's our two equations, and our unknowns in this case are c0 and c1, and we're going to solve for them in terms of u1 and u2. Okay, so the first equation leads to the following. It says u1 is equal to c naught plus c1 x1. And then the second equation is that u2 must be equal to c naught plus c1 x2. Okay? So I can pretty quickly solve if I just subtract them, and I can say that u2 minus u1, if I subtract this equation from this equation, the c naughts cancel, equals c1 times the quantity x2 minus x1, right? Which then leads to this, I've solved now for c1 being equal to u2 minus u1 over x2 minus x1. Okay, we can call that equation 4. So now I can just plug in C2 into either of these equations. I'll choose the first one. And I'll write down that, so just say substitute equation 4 into the first equation. Right? And if I do that, I end up with that U1 is equal to C naught plus U2 minus U1 over X2 minus X1 times X1. Right? So I can go ahead and just solve for C naught here and say that C naught must be equal to U1 minus U2 minus U1 over X2 minus X1 times X1. Right? And let's call that equation 5. So now I'm going to just substitute equations 4 and 5 into equation 3. And when I do that, I'm going to end up with that U star as a function of x is going to be equal to this C naught term, which is U1 minus U2 minus U1 over X2 minus X1 times X1, right? That's C naught. Then I have plus C1, which I said was U2 minus U1 over X2 minus X1 times X, right? Okay, so let's go ahead. I'm gonna expand to and then group according to U1 and U2. So here's my expansion level. So if I expand, I have U1 minus U2 X1 over X2 minus X1 plus U1 X1 over X2 minus X1 plus U2x over x2 minus x1 minus u1x over x2 minus x1. Okay? Now I'm going to go ahead and collect terms that have factors of u1 and then also factors of u2. So let's pull out the ones that have u1. And that gives me 1. Let's see. Then this term has a u1, so that'll be plus x1 over x2 minus x1. And then this term is going to be minus x over x2 minus x1. And then I can group the other term. Here's u2. If I group that term, let's see, this term has looks like negative x1 over x2 minus x1. And then this term is plus x over x2 minus x1. Okay? So let's do a little bit with this term. Let's give it a common factor. So we'll multiply by x2 over x2 minus x1 over x2 minus x1 here to make that 1. So we can write this whole thing as u1. And then now this becomes x2 minus x1 and then plus x1 minus x all over x2 minus x1, okay, plus u2 times x minus x1 over x2 minus x1, right? These x1s cancel, and I'm left with the following relatively simple form now that says this is x2 minus x over x2 minus x1 plus u2 times x minus x1 over x2 minus x1. right? Let's call that equation 6. So in this, and I'm going to go ahead and bring down this term here. This is the u star of x, right? This is the linear interpolation of this displacement. So this term we'll call this n1 of x. That's the first interpolation function. And this term is the second interpolation function. Okay, so it's just that simple. And we can write these in vector form, right? We could write this as n1 of x, n2 of x, transpose, times u1, u2. Okay? If we're going to use the same notation as we did in 2, so I'll just say in the same notation as equation 2, okay, so in the same notation as equation 2, we would write that u star of x and t, and we're approximating it really, there's only one direction, right? It's just the x direction. So I'm going to put a subscript there on the 1. So u star of 1 of x and t, we'd write that as n as a function of x, which includes n1 and n2. So now I'm writing it a little more compactly. And then this term here would be u1 as a function of t if we wanted. Okay? Where if I wanted to define n explicitly, it's going to look like x2 minus x over x2 minus x1, and the second one will be x minus x1 over x2 minus x1. Okay? And I would then write this term, u1 of t, if I wanted to show its components, as u1 superscript 1, u1 superscript 2, where I'm going to use the superscripts to denote the node numbers. Okay? Okay, so we'll call this equation 7. Okay, I need to make an observation here. So just say that, observe from equation 1, okay, that all the interpolation functions are in the integrands, right? Okay, what that means is that we need to numerically integrate them. Okay, we're going to use Gauss quadrature for this. And that's important because Gauss quadrature is defined over a particular domain. So Gauss quadrature is defined over the domain from -1 to 1. And that's in each dimension. Okay? So any element that has its domain going from -1 to 1 in all its dimensions, we refer to that element as being in its natural coordinates. So if an element is in this domain, maybe I say is defined on this domain, okay, it's said to be in its natural coordinates. Okay? Okay, so when we look up element types, whether they're truss elements or quadrilaterals or brick elements, each element is going to be defined. If you look it up in a book, it's going to be defined in its natural coordinates when we talk about its interpolation functions. Okay, so we're going to do the same thing for equation 7. Okay, so for each element type, interpolation functions are tabulated in natural coordinates. Okay, and so if you might be thinking, well, how am I supposed to integrate something in the real space when I'm given interpolation functions in natural coordinates? And the answer is we have to actually map the elements from the real space to the natural coordinates for the purpose of integration. Okay, so and we'll do that not in this lecture, and we'll show how to do that in a subsequent lecture. Okay, so what we do is we map the elements from the real space to the natural coordinates for the purposes of integration. So in the case of the 1D element, in the natural coordinates, you can look at, if I scroll up here really quick, you can take those interpolation functions, and it's as simple as plugging in -1 for x1 and plugging in 1 for x2. And if we do that, we end up being able to define our interpolation functions. So this is now n. And when we talk about natural coordinates, we'll use a different variable. Instead of x, I'll use xi. And in this case, it'll be defined as 1/2, 1 minus xi, and then 1 plus xi. Okay? So those are your interpolation functions in natural coordinates. And then just for the sake of completeness, I'll remind you here, this is U1 element, and that this has two components to it, U1 of node 1 and U1 of node 2. Okay? So remember that when I'm using Greek variables xi, eta, and zeta, I'm talking about natural coordinates. So this indicates natural coordinates. Okay? We'll call this equation 8. Okay? For a 2D quadrilateral element, okay, and this is going to be a 4-node quadrilateral. Okay? We have, let me draw the picture for you here. So here's our element. It's supposed to be square. And we have one axis, that's the xi axis, and our corresponding y-axis becomes the eta axis. And we have nodes 1, 2, 3, and 4. Okay? So if this is what our element looks like, this is in natural coordinates because we go from, this has a value of 1. If I were to project this down there, it would intersect at -1. Xi, the element intersects the positive xi at 1, and it intersects the negative xi at -1. Okay? So now if I give you the interpolation functions here, we're going to have two variables, not just xi, but eta and xi. So there's xi and eta. Okay? And you're going to detect a pattern. So we had 2 nodes in the 1D case, so we had 1/2. We have 4 nodes here, so we have 1/4. Okay? So you have to forgive my squiggly there. And now this becomes 1 minus xi, 1 minus eta. And you can derive them exactly the same way that we did before. It just becomes algebraically cumbersome to try to do in a quick lecture. So I'm sure there are other videos out there that can walk you through that process. It's not hard. Okay? And then this is 1 plus xi, 1 plus eta, and then 1 minus xi, 1 plus eta. Okay? And then I'm just going to give you one direction, so I'll give you the same sort of thing. So this is the U1 term. In this case, there's a U1 and a U2 term, but I'm just going to give you the U1. Okay, the U1 term is obviously U1 of node 1, U1 of node 2, U1 of node 3, and U1 of node 4, right, as expected. Okay, so I'll just say here that as a note, that U2 star can be approximated in the same way, except the subscripts on the displacement, instead of being 1s, would be 2. Okay? Okay. And the final case that I want to give you is for the 3D 8-node brick, which is what I'm going to ultimately want you to write your MATLAB FEA code in. Okay? So for a 3D brick element, this will be an 8-node. Okay, and I didn't want to try to draw this on the fly, so poof, the magic happened, and you can see I have 8 nodes, 1, 2, 3, 4. That was the same as the quadrilateral, and then I have 5, 6, 7, 8. Now I have xi and eta and zeta directions. Okay, So if I have an element that looks like this, then my interpolation functions are now going to be functions of xi, eta, and zeta, and they're going to look as follows. So you have to just forgive me as I keep kind of right here. So they're going to follow the same pattern. 1 minus xi, 1 minus eta, 1 minus zeta. The next term is going to be 1 plus xi, 1 minus eta, 1 minus zeta. Okay? And I'm going to just write these down for you, and you can pause the video and copy them down if you want. Okay, so there you have it. And similarly, I'm just going to write the first term for the x direction vector. So u1, just to give you a flavor for what that looks like. There'll be 8 terms in it. And we'll run from u1 node 1, u1 node 2, ... up to u1 node 8. Okay? So there are 8 x displacements, 8 y displacements, 8 z displacements in here. So there's actually 24 degrees of freedom in this element. But we'll talk more about that as we go along. Let's call that equation 10. Okay? So now you have the background on interpolation functions. Now we want to use this information to go ahead and continue to solve that weak form with the Galerkin applied to get to our approximation, our matrix equations that we're going to actually use to solve for an FEA solution.